this question, which is question 37 from the GATE 2021 AA paper, we are given a counter that is supposed to count through the following 3-bit gray code sequence, and we are asked to find the logic expression for the D1 input for this counter design. Underneath the question, you will find the title of the NPTEL course or video relevant to this topic. In this question, we are given the following 3-bit gray code sequence, and we are asked to construct a counter using 3 D flip-flops that repeats or enumerates this sequence periodically. That is, after you start with 0 0 0 and you go till 1 1 1 from left to right on this sequence, and then you cycle back to 0 0 0. That is repeating periodically. And so for a counter that is constructed to do this job, what is the logic expression for D1? This is what we are asked to find out. So before I go into the design of this counter, let us just look at the kind of sequential circuit that we are supposed to design. The idea is that there are 3 flip-flops, 3 D flip-flops, that is the input D1, D2, D3, all sharing a common clock, right? So I'll just write it as clock. With outputs Q1, Q2 and Q3. And the idea is that there is a combinatorial circuit here that accepts these 3 outputs and determines what the 3 inputs are supposed to be, so that as a result of this determination, the outputs Q1, Q2 and Q3 will cycle through the gray code sequence. The idea is that if we treat Q1 as the if we treat Q1 as the we have Q0, we don't have Q3, Q2 and Q1. You have Q1, Q0, Q1 and Q2. So we've got Q0, Q1 and Q2, and similarly D0, D1 and D2. Right? And treating Q0 as the LSB of the gray code and Q2 as its MSB, we will find that if the combinatorial circuit is such that on accepting, let's say 0 0 0, if the output of the combinatorial circuit for these inputs is the gray code sequence 0 0 1, that is the next thing in the gray code sequence, then as soon as the clock hits, the output Q0 will become 0 0 1 0 0 1. That is, whatever comes here is the next state over here, and it is the state of the counter, that is this outputs of the D flip-flops, that is supposed to cycle through the gray code sequence. So this is the goal of the counter design. So now let's proceed methodically, and of course, to just reiterate this point, for the input 0 0 1 to the combinatorial circuit, we would want the output to be the next number in the gray code sequence, which is 0 1 1, right? 0 1 1. So if we want that as the next output, it should come as the D inputs. So that is the job of the combinatorial circuit design. So as if you were to give one input of the gray code as as the combinatorial circuit's input, the next output of the gray code should come as its output. So now let's go forward and proceed with the design of this combinatorial circuit that does this job. So we simply build the state table for the counter, which involves the current state, next state, and the D inputs that are required to obtain the next state. If we were designing with something like a JK flip-flop, we would have to determine the JK flip-flop inputs that would be required to obtain the required next state for a given current state. So in this case, it's a D flip-flop based design, so it's very simple. We simply list the gray code sequence here, right, and we shift it up by 1, right. The reason we shift it up by 1 is because for this input we want this to be the output, that is, we want that to be the next state, and so we're just going to take that as the output of our combinatorial block. Remember, the output of the combinatorial block are the D inputs, is what serves the role of the D inputs. So we will simply upshift the gray code sequence and rewrite it on the previous row, right? And of course, since the final row will go here, this is where the periodic definition comes in. The idea is that for the last input of the gray code sequence, the next state is for it to wrap around, right? Now with these inputs and these next states requiring these D inputs, we will find that D1 has the following SOP expansion, canonical SOP expansion. It includes only the minterms 1, 3, 2 and 6, right? You just see the places where it's a 1. It corresponds to 1, 3, 2 and 6, and performing a K-map reduction on this, we will get the following expression for D1. This corresponds to the answer C, which is the correct answer for this problem.